Okay, so what we're going to be doing today is I have one more type of balancing chemical equation I want to introduce. And then I'm going to give you several equations for you to balance. So that's going to be the main focus for today, is for you to get practice balancing those chemical reactions. Excuse me. At the very end of today, I do plan on taking the balanced chemical equation and explaining what it means with respect to stoichiometry, which we actually started. Now, some other items. Number one, you do have a homework that's due today. It is over the stuff we went over last week. So it's not over balancing chemical equations. It's over the stoichiometry that we were doing with the formulas of chemical compounds. Number two, if you attended the conversations with chemists on Thursday of last week, you owe me some notes if you want your bonus points. And so while you're balancing chemical equations, while you're doing that practice, you can bring those notes up. Speaking of, if you have items that haven't been picked up, then while you're practicing those balancing chemical equations, you can come pick up those items. I have them on my desk. So in other words, if you weren't here last Thursday, for example, I have exam 3 for pickup and stuff of that nature. Thursday, you will have a quiz on active, and Thursday's class, we will be focused on reaction calculations. So we'll be using the balanced chemical equations in calculations. Any questions for me over what's going on this week? For the most part, it's a normal week. Okay. But the main reason I did want to go over even the homework assignment and the quiz is because we haven't had one in a couple of weeks due to spring break. So I wanted to take the time and remind everybody of those items. Okay, so balancing chemical equations, I'm going to start with a simple one, and then we're going to get into I'll do the more complicated one. The main reason I want to start with a relatively simple one is because of the fact that I want to get your minds up and running about balancing chemical equations before I throw you to into the more complex problem. So we're going to do a fairly straightforward one. Let's do CS plus N2 goes to form CS3N. Okay. So the first thing you do is just review the reaction to determine if there's any polyatomic ions that are involved. In this particular case, there are not, and therefore we're simply going to list out the information, the elements that are present. So we have cesium and we have nitrogen. On the reactant side, we have one cesium and we have two nitrogens. On the product side, we have three cesiums and we have one nitrogen. Because the two sides are not equivalent, this is not a balanced chemical equation. Now, I'm going to balance the cesium, or let's see, I'm going to balance the nitrogen first. Again, it does not matter, but you may have to go back and forth in balancing. So I have two nitrogens on the reactant side. I have one nitrogen on the product side. To make the two sides equivalent, I need to multiply the product side by 2. Whatever you multiply by becomes the coefficient for that formula. As a reminder, when you place a coefficient in front of the formula, that coefficient is telling you how many of each molecule is present. So now I have 2 cesium nitrides. So yes, I did wind up with 2 nitrogens, but I also now wound up with 6 cesiums on the product side. Now I'm going to balance the cesium. On the reactant side, there is 1. On the product side, there are 6. In order to balance the two, I have to multiply the reactant side by 6. Whatever you multiply by becomes the coefficient. So the balanced chemical equation is 6 cesiums plus nitrogen gives you 2 cesium nitrides. Any questions? Like I said, that one was hopefully not too bad, but I wanted to get our minds going again on the process for balancing a chemical equation before I tried to blow your mind. Okay. The next type of reaction that I'm going to do is called a combustion reaction. A combustion reaction is going to be a reaction of a reactant with oxygen. The most common type of reactant that is used in a combustion reaction is going to frequently be a hydrocarbon. Of hydrogen and carbon only. Now, if you have a combustion reaction with a hydrocarbon, then the complete burn will produce carbon dioxide, and water. I call it a complete burn because an example of a combustion reaction is the burning of octane in your gasoline tanks. If it burns clean, if it burns completely, then the only products would be carbon dioxide and water. But we know from our past education that if you start up a car, for example, in a garage, you're going to suffocate due to carbon monoxide. That is meaning that occurs because the burn is not clean or complete. So there are side reactions that can go on. But if you have a complete burn, a pure burn, a clean burn, then the only products would be CO2 and water. And that was supposed to be water. I hate when it changes things on me. Okay, so let's just look at octane. Octane is, the combustion of octane is C8H18. If it's combustion, that means one of the reactants is oxygen. And if it's a clean combustion, a complete burn, then the two products are going to be carbon dioxide and water. Step number one in balancing this equation is we're going to evaluate the equation. We're looking for polyatomic ions primarily, and there are no polyatomic ions here. So that means we're going to list out our elements. We have carbon, hydrogen, and oxygen. On the reactant side, we have 8 carbon, 18 hydrogens, and 2 oxygens. On the product side, we have 1 carbon, we have 2 hydrogens, and we have 3 oxygens. We have 3 oxygens because carbon dioxide contains 2 oxygens and hydrogen contains 1 oxygen. When you add that together, that means you've got 3 oxygens. Now, we begin to balance. And if you'll recall, one of the things that I gave you a hint about is you're going to balance an element that appears in only 1 compound on the reactant side and only 1 compound on the product side first. So we're going to balance our carbon and hydrogen because that rule, we'll balance those first. Also, in those hints, though, I said save compounds that consist of only 1 type of element until last. So as a second reason why we're going to not balance the carbon and the hydrogen first is because oxygen appears in a compound by itself. So we'll save the oxygen till last. Okay, so we begin. On the reactant side, there are 8 carbon. On the product side, there are 1. To get 8 carbon on the product side, we multiply the equation by 8. Whatever you multiply by becomes the coefficient. Now, if I were to write out all of those carbon dioxide molecules, all 8 of them, you would see that, yes, we wound up with 8 carbon dioxides. But in the process, we wound up with 16 oxygens. In other words, we have 8 times 2 oxygens from the carbon dioxide. So that means we are now up to 17 oxygens. Now we balance our hydrogens. On the reactant side, we have 18 hydrogens. On the product side, we have 2. To make the 2 sides equal, we need to multiply the product side by 2. Whatever you multiply by becomes the coefficient. Now, if we were to look at this, Yes, we wound up with 18 hydrogens, but we also wound up with 9 times 1 oxygen from the water, or 9 oxygens, meaning we now have 25 oxygens on the product side. Okay, so our carbon and hydrogens are balanced. Again, we balance those first because they appear in one reactant and in only one product. Now we're left with oxygen, and we balance it last because it's in a compound all by itself. The question is, what do I need to multiply by 2 to get 25? Yes, what, we'll come to that in just a moment. What would the decimal be?
12.5.
Okay, so we would need to multiply this by 12.5, which will give us the 25. Whatever we multiply by becomes our coefficient. Now, as you were pointing out, the last statement in balancing chemical equations is that the coefficients must be in the smallest whole number ratio possible. So this equation's not allowed. Even though everything's balanced, this equation is not allowed because you don't have everything in a whole number. So what we do when we come across this is we go, okay, what do I need to multiply the entire reaction by to get everybody to a whole number? What do I need to multiply 12.5 by to get to a whole number? Two would work. So we're going to multiply the entire reaction by 2. When we multiply the entire reaction by 2, you get 2 C8H18s plus 25 oxygens goes to form 16 CO2s plus 18 H2O. And now you are balanced. And you have your coefficients in the smallest whole number ratio possible. This is the toughest type of balancing chemical equations I'm going to give you. But as I mentioned on Thursday, balancing chemical equations is a lot like a puzzle. I can give you hints, I can give you places to start, but it does come down to you just doing them. And sometimes when you balance a chemical equation, you're going to balance it or you're going to work at it and nothing seems to want to happen. In other words, you can't get it balanced. So sometimes you just have to erase everything you've done and start with a different element. It's like up here on this equation, I could have started with the cesium, but if I'd have started with the cesium, I would have had problems with the nitrogen. So I would have wound up erasing everything and going, okay, instead of cesium, let me start with the nitrogen. And it would have fallen into place. Balancing chemical equations is a lot like a puzzle. Sometimes it's going to be really easy. Sometimes you're going to do a lot of erasing. So now what I'm going to do is I'm going to give you some balancing chemical some equations to balance. And that is what we are going to focus our attention on for the remainder of this, for the majority of this class, is you working at balancing these equations. I think did I give you this one already? Oh, well, if I did, it's good practice. And again, if you were absent on Thursday of last week when I passed back your exams, you can come get them while you're working on balancing these. And also, if you have notes for me, you can bring them up. Okay, let's look at these. So the very first one, I did give you the answers. It's 10 sodium plus 2 sodium nitrates goes to form 6 sodium oxides and a nitrogen. When you wrote out first of all, I did look and there was no polyatomic that was on both sides of the equation. So that's why I listed out each element individually. There were 2 sodiums, 1 nitrogen, and 3 oxygens on the reactant side. On the product side, there were 2 sodiums, 2 nitrogens, and 1 oxygen. I started by balancing the nitrogens. When I balanced the nitrogens, that gave me 2 sodium nitrates, which altered not only the nitrogen, but it also altered the number of sodiums. At that time, there was 1 sodium from the first reactant and 2 sodiums from the second reactant. And so that was a total of 3 sodiums, and there were 6 oxygens. Then I balanced the oxygen, and the reason I balanced the oxygen next is because it appears in only 1 substance on both sides of the equation. I balanced the oxygen by multiplying the product side by 6. Whatever I multiplied by became the coefficient, but in doing so, that also gave me 12 sodiums. Now, this is where it got a little tricky on this particular problem, and that is we did not want to alter the 2 sodiums from the sodium nitrate. You didn't want to alter that because if you altered the sodium nitrate's coefficient, you would have altered the nitrogen and the oxygen. So we had to keep 2. So what I did is I took this 12 and I subtracted out 2 and said, okay, I got to have 10 come from the original sodium, and that's where the 10 came from. The next one, the secret to it was remembering that you can think of water as HOH. And when you think of water as HOH, you would see that you have hydrogen, phosphate, magnesium, and hydroxide on both sides of the equation. On the reactant side, I had 3 hydrogens, 1 phosphate, 1 magnesium, and 2 hydroxides. On the product side, I had 3 magnesium, 2 phosphate, 1 hydrogen, and 1 hydroxide. Because hydrogen and oxygen appear in multiple equations, I started with the magnesium and the phosphate. So I multiplied the magnesium through by 3 on the reactant side. Whatever I multiply by becomes the coefficient. But that 3 also meant I now had 6 hydroxides. I then did the phosphate. On the reactant side, I had 1. On the product side, I had 2. So I multiplied the product side by 2. Whatever you multiply by becomes the coefficient. But in getting 2 phosphates, I wound up with 6 hydrogens. So I have 6 hydrogens on the reactant side. I then multiplied the product side by 6 to get 6 hydrogens on the product side. In so doing, I wound up also with 6 hydroxides. Questions? Just like with the previous one, it's easier to think of the water in this case as HOH. Folks, think of water as HOH anytime you see a hydroxide on the reactant side and water on the product side, or vice versa. 99% of the time, it will come out in your favor. So when you made your list, you had aluminum, hydroxide, hydrogen, and carbonate. You had 1 aluminum, 3 hydroxides, 2 hydrogens, and 1 carbonate. On the reactant side, on the product side, you had 2 aluminums, 3 carbonates, 1 hydroxide, and 1 hydrogen. I'm balancing the aluminum first. So you multiplied the reactant side by 2. Whatever you multiplied by became the coefficient, but in so doing, you wound up giving yourself 6 hydroxides. I then took care of the carbonate. On the reactant side, I multiplied the carbonic acid by 3 in order to get 3 carbonates. But in doing so, I wound up with 6 hydrogens. So then I multiplied the product side by of the hydrogen or the hydroxide by 6. And in doing so, I wound up with 6 of the other. Questions? Let's get some more example or practice. Let's do C4H10 plus O2 goes to form CO2 plus water. Let's see. Let's go with Al plus S8 goes to form Al2 S3. And Rb plus RbNO3. Oops, no parentheses. Goes to form Rb2O plus N2. Okay. So the first equation where you burned butane using combustion, this was essentially identical to what I did with the octane. And you could have gone through the process balancing the carbons and the hydrogens. And in so doing, you would have come up with an odd number for your oxygens. So you had to multiply the entire equation through by 2 to get it to where it was all a whole number ratio. The aluminum and sulfur, I chose the sulfur because I saw 8 sulfurs on the reactant side and 3 on the product side. And I'm like, okay, an even number, an odd number, I'm going to start there. So I balanced out the sulfurs first. And the lowest common number that 3 and 8 have together is 24. So that's why I multiplied the S8 by 3 to get 24 sulfurs and the Al2S3 by 8 in order to get 24 sulfurs. Now, in getting 24 sulfurs on the product side, I also wound up with 16 aluminum, so I multiplied the reactant side by 16. And then the last one was identical to the other problem that I did, I don't know, today, where you first needed to balance out your nitrogens, then your oxygens. And what that would have given you is 3 rubidium on the reactant side and 12 rubidium on the product side. Because you cannot change the rubidium nitrate at this point without altering the nitrogens and the oxygens, that meant that that too had to stay constant. So we took out the 12 minus 2, so that left us 10, and that's why there's 10 rubidiums. Questions? Okay, so what do the coefficients mean? In a balanced reaction? Well, I've already talked about it to some degree. One possibility is we can talk about individual molecules. And this was useful when balancing the equation. So basically, we would say, okay, there's 10 rubidium atoms to 2 rubidium nitrates to 6 rubidium oxides to 1 nitrogen molecule. Again, this particular variation of this description is useful when balancing the equation. But we cannot, a single molecule is too small to manipulate. A single atom is too small to manipulate. So this particular variation is really only valid for balancing chemical equations. So what else can we do? Well, we can, instead of talking about them in terms of molecules and atoms, we can talk in terms of moles. So the second way of multiple ratios. Now this method is extremely important when we're dealing with stoichiometry, which is the mathematics associated with balanced chemical equations. And in this case, it would be 10 moles of rubidium to 2 moles of rubidium nitrate to 6 moles of rubidium oxide to 1 mole of nitrogen. Again, we're going to use this second method of discussion when we're dealing with stoichiometry, which is calculations for balanced chemical equations. So, an example. How many moles of rubidium oxide can be formed from 12.5 moles of rubidium nitrate? Yes. What now? Now, just like with our previous math problems, we're going to list out what we were given. We were given 12.5 moles of rubidium nitrate. We list out what we want to solve for. We want moles rubidium oxide. The formulas are different. What have we been saying every time formulas are different? What type of conversion are we going to use? If the formulas are different, you always use a mole to mole ratio. If the formulas are different, you always use a mole to mole ratio. Now, the fact is we now have 2 places to get our mole to mole ratio. The mole to mole ratio that we've used in the past was where we were talking about an element within the compound. This time, our mole to mole ratio is going to be 2 compounds within a balanced reaction. But anytime you're dealing with 2 different formulas, you've got to use your mole to mole ratio. So we know that 12.5 moles, or excuse me, no, balanced chemical equation. We know that 2 moles of rubidium nitrate is in a ratio with 6 moles of rubidium oxide. I know I keep repeating this, but again, we knew we had to use a mole to mole ratio because the compound formulas were different. There are two different places to get mole to mole ratios, and it depends upon what you're working with. One place to get a mole to mole ratio is an element within a formula. That's when you're working with an element in a formula. But the other mole to mole ratio occurs when you're working with a balanced chemical reaction. And when you have a balanced chemical reaction, the coefficients are your mole to mole ratio. The next thing we look at is our unit, mole. Hey, we already have mole because we have a mole to mole ratio. We're looking at mole. We already have a mole because we're looking at a mole to mole ratio. So in this particular case, we'd start with what we were given, which is 12.5 moles of rubidium nitrate. And our conversion factor is going to be the mole to mole ratio. Of that mole to mole ratio, we're going to place 2 moles of rubidium nitrate in the denominator so that our unit and substance will cancel out. The other half, the 6 moles of rubidium oxide, will go in the numerator. And when you do this calculation, you get 37.5 moles of rubidium oxide. So what's the takeaway for today? The takeaway for today is balancing chemical reactions. Anytime you have a reaction, that is your first step. Make sure it's balanced. The second takeaway is, what do the coefficients of a balanced chemical reaction mean? The most useful of its meanings is as a mole to mole ratio. Now, I did a calculation at the very end. I don't want you to worry about that calculation as much today, because what we are going to do for the next 2 classes is we are going to do stoichiometry. And we are going to use all of our knowledge about chemical calculations to this point. And hopefully you'll start to see the patterns starting Tuesday in these chemical calculations. Any questions? If not, don't forget you do have that homework, and I will see you Thursday.